Okay, this is topic 6. It's centered on probability distributions. So, probability distributions can be used to quantify the likelihood of occurrence of all possible outcomes. So, we already talked about what random variables x are. The x is in capital for the random variable, and these probability distributions which we looked at have this random variable on the x-axis, and then the y-axis could either be frequency for PDFs, which is probability density function, or the y-axis could be probability that goes from 0 to 100% for cumulative density functions. So there are two main classes of probability distribution, and it all depends on whether variable x is discrete or continuous. Discrete being like integer values, so 0, 1, 2, 3, 4, and so on. You can't have any fractional numbers. And continuous means x could assume any number on the real number line. So it could be 0.001. It's infinite number of points between the minimum value and the maximum value. So that's the main difference between discrete probability distribution and continuous probability distribution. With discrete probability distribution, with discrete probability distribution, the random variable x has only a finite number of values. For instance, in the coin tossing experiment, there is only two possible outcomes, head or tail. And then for rolling a die, 6 finite outcomes, 1 through 6. So those are discrete probability distributions, and examples of these include binomial Poisson and multinomial distributions. But as petroleum engineers, we'll be working more with continuous numbers like porosity, permeability. These are all continuous numbers. So we will focus on continuous probability distributions. And these are associated with random variables that can take on infinite number of values, because the numbers could be any number on the real number line, and then you have infinite number of values. And then these examples of continuous probability distributions include normal or Gaussian distribution, which both mean the same thing, log normal, which we will learn about today, and then uniform probability distribution, which we learned previously. So does anyone remember the function we use in Python for normal distribution? The function comes from the NumPy package. For normal distribution is numpy.random.randn, which stands for normal distribution. And precisely that function gets you a standard normal distribution, which is a normal distribution with a mean of 0 and a standard deviation of 1. How about uniform probability distribution? How do you get that from NumPy? NumPy.random.random, and that will give you random numbers between 0 and 1. So we already talked about uniform and normal distributions in the previous topic, but we'll summarize it and then move on to talk about log normal distribution. And if we have more time, we'll talk about triangular probability distribution. Good. So these are some of the most common continuous probability distributions. The uniform probability distribution assumes that all outcomes are equally probable, which is why the frequency is constant, because any realization of x has an equal chance as all other realizations. And like I said, you get that from numpy.random.random. Very useful function. It's typically applied in Monte Carlo simulation, and we'll talk about Monte Carlo simulation shortly. That's a complex sounding name, but it's really a simple probabilistic process. So normal distribution is also known as Gaussian distribution, and it's characterized by only two variables, mean and standard deviation. More precisely, those are two parameters. So it's characterized by two parameters, which are the mean and standard deviation. From central limit theory, if a variable is the sum of independent and identical distributions, it will be normally distributed. So independent and identical distribution, we typically use the short form IID for independent and identical distribution. What are independent probabilities? We already talked about that. It means probability of A given B is equal to probability of A, meaning that the condition that B took place already doesn't change the probability of A. So those are independent distributions. So if you sum up a normal distribution and another normal distribution, what you get will be a normal distribution, and that's based on the central limit theory. Most random distributions in nature tend to be normally distributed. For instance, the distribution of ages of human beings. If you go calculate that, take a sample, you'll realize it to be normally distributed. The height of all human beings will be normally distributed. But if you go grab the height of students in kindergarten, then of course it's not going to be particularly normally distributed because the range is going to be very tight, right? But in general, totally random events, when you plot their distribution, they tend to be normally distributed, and that also comes from the central limit theory. The probability density function for Gaussian or normal distribution is given by this expression right here. So it's exponential, and you don't have to memorize this. This is already taken into consideration by the NumPy package. This equation can be numerically integrated to obtain the cumulative density function. So this is the PDF, right? Probability density function. And you can integrate that to get the CDF, where the y-axis now goes from 0 to 1. And that's the form we typically use in stochastic modeling. Why? Because probabilities go from 0 to 1. And so when you integrate the PDF and then you obtain the CDF, which goes from 0 to 1, and then the y-axis will be probabilities. The mean, median, and mode are all equal, right? Because for normal distribution, it's totally symmetrical. I've sketched it several times, and you'll still see some sketch on the next page. It's symmetric. This shows it in the form of histograms. So it's symmetric. The mean, median, mode are all the same. These are some facts about the normal probability distribution. Like I said earlier, it's specified completely by only two parameters. It's the mean and the standard deviation. If the mean is 0 and the standard deviation is 1, like I said, what you have is a standard normal distribution. And normal distributions have these properties. So whether it's standard normal distribution or the regular normal distribution, where x, the random variable, can assume any value, we know that 68% of the data, which is what is shown in this green color, right? 68% of the data will lie within one standard deviation. So sigma is the standard deviation, mu is the mean. So to the left and to the right, you're one standard deviation away, plus or minus one standard deviation. About 68% of the data will be in that interval. How about if you're two standard deviations away, from the left and from the right? So it's both this green shaded color and this light blue shaded color. So this is one standard deviation, this is two standard deviations to the left, this is two standard deviations to the right. That entire area will account for 95% of the data in standard in normal distribution. And lastly, when you have three standard deviations to the left and to the right, it's all of the shaded regions from the purple all the way to this other purple. 99.7% of your data will lie within that interval, and that's very high. And subsequently, you will see how we use this information. It means when we are doing sensitivities, we can assume for all practical purposes you will be within within 3 standard deviations from the mean. Good. So those are some key properties of the normal distribution. I'll continue with the CDF in the next video.